Hello guys, for today's lab we are going to execute the microcontroller lab program. So that is uh, program number 8, which is program to count number of ones and zeros in two consecutive memory locations. So for this we are going to use Keel software, and we are going to select the evaluation board, that is LPC2148. So what is the program? So program is to count the number of zeros and ones in two consecutive memory locations. So we are going to store some values in the memory locations, and we are going to count the number of zeros and ones in these memory locations. Okay, so I have taken these values. So this is first value and this is second value. So since we are using a 32-bit microcontroller, so this value, each memory location will be having a 32-bit memory location. So when we convert this hex value to the binary, so this is what we are going to get. And here you can count the number of zeros and number of ones. So when we count, we have number of zeros 23 and number of ones 9. Okay. And when we count the number of zeros in the second value, we have number of zeros 20 and number of ones 12. So when we consider two consecutive memory location, that is memory location and 1, so the number of zeros we get is 43 and number of ones we get is 21. Okay, so we are going to verify whether our program works fine or not. So we'll see what's the logic behind this particular program. So the main logic here for this program is we are going to use the rotate instruction, a rotate right instruction. So what is this rotate right instruction? So you can see this is the rotate right instruction. So we are going to give an immediate value to this rotate right instruction. So what happens when we give here ROR followed by some value? So what it means? So we are going to move the bits for this n number of positions. Okay, so where n is the number of bit positions to rotate in the range. So in the range 1 to 31. Okay, so let's consider an example. Say suppose I'm using ROR comma #1. So what it means? So I'm going to move the this memory locations, the bits, to the right side by one position. So when we move by one position, you can see that B0 will be placed at the 32nd position, and the value which was there in the 32 location, that will be moved to the 31st location. Okay, and also you can see that the B0, it will be uh, moved to the carry bit. Okay, so this is how the ROR instruction works. So if we give #2, what it means? So it means that we are going to move these bits by two positions towards right. Okay, yeah. So in this program we are going to use RORS. So S indicates, yeah, so this is an suffix with ROR instruction. So suffix, when we use this suffix S, so it is what it will do is it will update the conditional flags. Okay, so when we are going to write S here, so using this S, so what it will do, it will update the conditional flags. Yeah, so that is the logic. So we'll begin with the area. Okay, so this is the area that I have defined, and this is the name of the this particular area, and this area is for code, and it is read only. Okay, and next we are going to enter this area and start to indicate that this is the start of execution. Okay, so in the question it is asked two consecutive memory locations. So in order to know in which memory location I am, so I'm going to initialize this R0 to 2. Okay, so the question is for two consecutive memory locations, so I have initialized as 2. And R3, R4 I am using for counting the number of R3 I'm using for counting 0. Okay, and R4 I'm going to use for counting 1, number of 1. Okay, and so next I need to store, I need to take the first, I need to take the value from the memory location and store it into the register. So for that I need the address where exactly this particular variable is present in the memory location. So this variable I have declared in the data section. Okay, so area data1 data read only. So I have initialized values here, two memory locations. Okay, so first I'm going to read the address where exactly these values are stored. So I'm going to read the first value. Okay, yeah, I'm going to yeah, I'm taking the address into the register r1. Okay, so equal to indicates this that I'm going to get the address where this memory location is present. So address is stored in r1. And next, what I'm doing, I'm going to read the first memory location value. So this is how we can use the LDR instruction. So LDR R2 comma, in the square bracket we need to mention the address and hash 4. So it will what this is post index LDR LDR with post indexing. So it means that first I'm going to use the address and then I'm going to increment the base address by 32-bit. Okay, so first I'm going to read the first memory location into the register R2, and then R1 will be pointing to the next memory location. Okay, and then I'm going to check whether since I have read one memory location value, so I'm going to reduce the R0 by 1. Okay, so now earlier R2 R0 was 2. Now after subtracting by 1, so I have remaining is 1. And then I'm using move r5 comma hash 32. Hash 32 is used because it is the memory location I have defined as 32-bit value. Okay, so DCD, so it will store a 32-bit value. So if I use W here, so it means that it is a 16-bit, right? So and the program that I'm using DCD, so it is a 32-bit value. So how many rotations I need to do? So I need to do 32 rotations. So to keep a track, so I have this 32 initialized in the register R5. So what I will do, I will rotate whatever the value we have in the memory location which is stored in R2 by 1. Okay, so when I move rotate by 1 position, so if I use X, it means that the flags, conditional flags bits are updated. Okay, so when I move by 1 position, so the first bit, the 0th bit will be moved to the carry flag, right? And the first bit will be moved to the 0th position, right? Like that it will rotate, and depending upon the carry flag, so we are going to count the number of zeros and number of ones. So for that I'm going to use this ADDCC instruction. So it is add along with the carry. Okay, so if I'm using here extra C, so extra C indicates that so this particular add operation happens only if the carry bit is set to 0. Okay, so if the carry whatever the value in the carry bit we have, so if that value is 0, then only this particular instruction will be executed, otherwise it will be skipped. Okay, depending upon the conditional flag. And so if the value moved is 0, then we are going to increment R3. Otherwise, if the value is 1, if the value is 1, so that is added with by using this suffix s here. Okay, so R4 is incremented by 1 only if the carry flag is having the value 1. Okay, so these are the two instructions to count the number of zeros and number of ones. So once we uh, do we count for the first bit, then we are going to subtract r5 by 1. So yeah, we are checked for 1 bit, so we need to check for remaining 31 positions. So that's why I'm going to subtract R5 by 1. So this will be continued until what? Until I compare all the means I calculate for all the 32 bits. So once the R5 becomes 0, then I'm going to stop. So if it is not equal to 0, then I'm going to loop back. So I'm going to this particular label. I'm going to start executing from this instruction. Okay. So if it is equal, what it means that? It means that I have checked for all the 32 bits. So now I'm going to compare R0 comma hash 0. So how many memory locations I have checked? So initially we have done this for one memory location. So still R0 is having one value. So still it is not equal to 0. So again, if it is not equal to 0, we are going to back to this memory location. We are going to fetch the next value in the memory location, and then we are repeating this instruction. Okay, so we can see the execution here. Compiling, there are no errors. Build target, no errors. Yeah. So initially R0 is initialized to 2. So because of we need to check for 2 memory locations. Then I'm going to move the first value. So this is yeah, so this is the first value, that is 13072021. Okay, and I'm going to subtract R0 by 1. So I have used only one memory location, so another memory location I have to do. So first I will initialize the number of comparisons, so it is 32. So R5 is initialized to 20 x20, and you can check here CPSR. So what is the carry bit flag here? It is 1, right? So it is 1. Yeah, yeah. Now you can see that R3 is not incremented because the carry bit flag is 1. So R3 should not increment. You can see that this instruction is not executed. So still we have 0 because the carry bit flag is set. Now R4 has to be incremented because we are using S suffix here. So S suffix means we are going to add this value only if the carry bit flag is set to 1. So you can see that the R4 value is incremented, right? So then we are going to compare for we are going to reduce 32 by 1. So we have still 31 memory locations. Okay. So again, it will go back and start for the 31st bit. Okay, so this will be repeated until what? Until the R5 value becomes 0. Yeah, you can see that the R5 value becomes 0. So you can see the number of zeros, that is hex 17. So you can see when I count, it is number of zeros is hex 17 and number of ones is 9, which is there in the register R4. Okay, so this is with respect to first memory location. So I need to store the second memory location value. So you can see that when I compare R0 with the 0, okay, it is not equal, right? Because R0 is 1. Okay, so still we have another memory location. So that's why we are going to execute from this label, that is this label. So that is we are going to store the next value in the memory location to the register R2. Then we are going to repeat this instructions. You can see this is the second value. So again we are going to check for the next 32-bit memory locations. Yeah, so R5 became 0. Okay, and we will see. Yeah, so R0 we are comparing with a 0. So now R0 is a 0. So it will stop. Now it is not, it is equal. So it will skip and it will stop. Okay. So this is the result. So R3 we have 2B, which is in decimal we have 43. Okay. So 43 zeros. Okay, and number of ones we have 21. In the hex we have value 015. So 015. Okay, so this program is correct. Thank you.